Morning. Hey guys. How's it going? Okay, so the topic of this week is distribution and logic. So last week we looked at repetition, so basically creating a series of copies of something, and we could make rows, we could make grids, and we talked about kind of where repetition shows up in architecture and how that's an important idea. This week we're talking about distribution. So it's this idea that what are different patterns we could use to make copies. So we went from just making copies to now making kind of specific kind of targeted copies, and then applying logic in the form of culls. This is one form of logic to say we don't want some of those copies. You know, we want a specific pattern. And you guys saw examples of this in the lab and in the skills video. Today what I'm going to do is I'm going to do a brief review of some of the patterns that we have in Grasshopper for distributing objects and for logic. And then I'm going to talk about how to use those patterns, or basically where these patterns show up in some actual architectural precedents. And this is a really good way to learn like comp methods, or to learn these methods in general, is to take an architectural project and attempt to deconstruct like maybe how these ideas start to show up. What I'm going to do is I'm going to show you these patterns, because a lot of ways it's just basically about combining patterns that you already know or patterns that I'm going to show you so that you can get the result you want. Okay, I wouldn't expect you to figure this stuff out on your own, as it involves a lot of different like components that you might not have seen before, or some ideas you might not have encountered before. But by showing you the ideas and then by showing you it in a project, hopefully I make the connection between the pattern and that result. And then this could be something that you might actually apply in one of your projects, or maybe later on when you want something like that, you would at least be able to like think about, okay, what were the patterns that showed up in this project? So that's kind of what I'm going to do today. Before I go on, is there any major questions about the work in the lab reports? Do you guys want to talk about? Nothing? It's all clear? All right. Let me know later. I don't want to derail things, but this is a good time to talk about lab reports if you need it. Okay. So repetition, we talked about repetition shows up in architecture, but this is kind of a very simple like copy-paste, carbon copy repetition, right? You just take some element that we made, maybe something really intricate, and copy it a few times, okay? But we can do a little bit better than that with computation. We're going to be talking about our ideas like we see in this railing here. So, you know, this is a form of repetition, right? You have the railing, but it's being repeated through this what do you want to call it? This like stairway in a particular way. So there's a pattern here if you can see it. There's actually logic here, right? You've got A, B, A, B, if you count the space as a B in the rhythm. So it's not just like copying something. There's actually some kind of a logic in the way that that's copied. And there's some kind of distribution in the way that it's applied to the geometry. Okay? So already we see. And you can say that there's some kind of rhythm in how the top part of the railing interacts with the bottom part of the railing. And this is the kind of thing that you could pretty easily create. You could look at this thing parametrically and really do a lot of studies of it. Okay, and I showed you kind of an example of this in the skills video. But it's a good opportunity to kind of talk about what some of the general principles or patterns are of distribution. So first thing I'm going to do is just talk about the big idea of distribution, at least as it works in Grasshopper, is that you'd have some object. Well, basically that you want that points are a good place to place things. So I'll actually start with that. So if I just have a point object, if I go into my construct point here, and I have something like a cylinder. All right, so I have a point. If I plug that in for where my cylinder, where the base plane of that cylinder starts, if I move that point, I move that cylinder. Okay, and that's the simplest idea, the simplest demonstration of distribution. Wherever that point is, there's going to be a cylinder. And we saw examples of this where it's like if I have a lot of points, for instance, if I have a series, right? I get a lot of cylinders, okay? Pretty basic stuff. Then some of the things I showed you were I could make a curve I'm just going to draw like some kind of random silly curve here. And I can reference that curve. So instead of using numbers, basically, I can, and instead of using those numbers to make points, I can reference this curve. So now it's in the system. And I can even hide this now. And it exists in Grasshopper as a state. Right? It turns green. Okay? And I can do things like divide that curve. And now I can get points from that curve. And then when I have points, right, I get the locations of cylinders. And it's not just cylinders. It can be any kind of arbitrary object I want. It could be rectangles. You know, if I want to just drop a rectangle. Now I've got rectangles on that curve. Okay. And actually, this is going to be something that we're going to look at later. So I can do shapes. I can make some kind of arbitrary. Let's make a torus. I like them. They're like big donuts. All right. I can take a torus, and I can reference it as a B-rep. I haven't talked about that yet, but B-rep stands for boundary representation, which is essentially a surface, right? A surface represents a boundary. What's inside, what's outside, what's not surface, what is surface is a boundary representation. I can take any geometry I make. I can make a 20-story skyscraper, and I can reference it as a B-rep if I want to. Okay? So I take that B-rep, and I reference it, set one B-rep. Okay? Then I could do something like I could, so I've got points. I don't have any kind of thing I can plug into that just says, you know, like distribute it. What I can do is I can orient that B-rep. So what orient does is it takes some kind of geometry, and it takes whatever kind of initial plane that it's in, and it takes a final plane, okay? And it basically like distributes it. So I've got the points along the curve. I can use those points to make planes because that's what a lot of distribution does. So I'll just make XY planes. So I take those points, and now I'm distributing XY planes. See those? I can plug those in for. Now you can see it started to do something here, but they're not quite aligned correctly. That's because I'm not actually getting the plane that this object is on. So to do that, I'll take the volume of the B-rep, and that gives me the center of it. Remember, area gives me the center of a two-dimensional object. Volume gives me the center of a three-dimensional object. I can use this volume centroid to give me an XY plane. So now I have a plane that's at the center of that. And if I have the correct plane for both objects, they're going to be correctly distributed. Okay, I'll take you through that again. I went through it pretty quickly, but let me go ahead and hide this. So, actually, I'll do that. So I made a B-rep, right, which could be any kind of single kind of geometry or collection of geometry. B-rep is actually pretty like general. Everything in Rhino is basically, well, everything that you'd want to build is basically a B-rep. So I can reference it, and in order to distribute it, I looked at the orient object. So this is one that you guys might want to pay attention to. You can distribute any arbitrary geometry with an orient. Orient takes the geometry, that's G. So that one's pretty self-explanatory. And then it has a base plane, like initial plane. So that's wherever it comes from. And then a target plane, which is wherever it's going. And to get the target planes, I divided the curve, and then I used that to distribute planes on those points. And then to find the target plane, I found the volume, and I found I used that to make an XY plane. So I like distributed one plane, and then I propagated it across that. Now, what's cool about that is that it's actually fully parameterized. So if I divided that curve by more points, I would get more donuts, basically. And that's a pretty simple example, but if you were trying to place a series of trees around a park or something to follow a path, right? You could sit there and noodle with each one painstakingly, or you could divide something and then snap to each one of those things, right? Copy paste it. What if you didn't even know what the spacing was that you wanted, right? So you could use a technique like this, right, with your CAD lines or with your lines in Rhino, take your tree object, reference it, and just distribute it along there, right? So it's not just like railings or like other things like that. Like you can use this to really explore a lot of things. And so, you know, distributing geometry is really useful. Can be a really useful tool. That could be a three-dimensional, you know, line too, right? That's kind of what's going on here, isn't it? Like there's a line that's attached to the stair that's actually going up in space, right? We can reference that line, use that to create our railing. So it's not just that. You can think about things like suspension bridges, like, you know, these kinds of elements. Not that we're engineers, that we're really bridge designers, but, you know, if you're going to distribute the cabling on a bridge, that's definitely something where you can. Actually, let me show you an example of that really quick. Anybody have any questions about like this pattern here? Okay, so this is in the video, right? It's going to be posted. It's a pattern. So anytime this is like the distribute arbitrary geometry pattern, we'll call it. The main thing is to just be introduced to the orient component, and you can kind of like reverse engineer it from there. All right, I'm going to go ahead and kill this, and we'll start. I'll show you another kind of pattern, and we've sort of seen this before, I think, but I'll go ahead and talk about it now. So if I have, you guys remember the line SDL component? I think I introduced that in the video. So we've made lines before by taking 2 points and like connecting points together, like that makes sense. Or we've made curves by connecting a series of points together. Sometimes you just want to make a line that's a certain length, like you don't necessarily know where the end coordinate is. Kind of like a series where you know where you want to start and you know how long you want each step to be, but you don't know what the end's going to be. Same thing with an SDL line. Line SDL stands for start, distance, or start, direction, and length. That's pretty much all you need to know to make a line. So start is some point, and I could just do some arbitrary point. Oh man. Construct point, there we go. Okay, so some point, it's fine, I need a point. You can see already it's just like a little hair, okay? And if I wanted to distribute something, I could say like, okay, the direction is an X, so you want a vector for that. And then the length is the fun part where you put a slider in, you know, for the length. So I can go ahead and extend this. Now it becomes hard to see because it's actually in the axis, or on the axis. So you can do, there's a component called endpoints, and I can plug it in, and that just gives me the start and the end point, which is really nice if I want that. So now I can see where that end is. Okay, no biggie, all right? Okay. Then I think I showed you guys, so we did a thing that would actually like divide a curve into multiple segments. I showed you guys another one, another way to divide a curve, which is to find basically a point on a curve, which can be really useful. It never shows up. Let's see here. Point, curve, analysis, okay. They change all the names of everything on me. Okay, evaluate curve, point on curve, yes. All right, why is that so hard? Okay, if I plug that into the thing, I've got this slider here, right? And I can actually, you see how it's like 0.21. So the whole curve, no matter what length it is, 0 is the beginning of the curve, 1 is the end of the curve. So 0.5 is always the midpoint of the curve. There isn't like a midpoint component. It's point on curve with a 0.5. Okay, and you can right-click this guy. I showed you this in the video. You can go directly to its midpoint. So now I've got 3 points for that curve. There's a lot of different kinds of things we can do with, you know, like geometry when we have the endpoints and when we have the midpoint. Okay, and one of the things we can do is what I'm about to show you. So I go back to that NURBS curve, and remember how NURBS curves work, where they attempt to interpolate between multiple points, and they kind of make a smooth curve. Okay. I can take that midpoint and I can make a copy of it. I can move it in the z-axis by some arbitrary amount. So this is a lesson too. So what we're talking about is the sort of like, this is actually like the topology of a line. Do you guys know what I mean when I say that, like topology? So like basically lines are made out of points, surfaces are made out of lines, okay? And then you can get points from a surface if you know where the lines are. We'll like talk about this more, but we have a line, I'm able to extract extract points from it, then I can transform those points into something else, and I can make new things. So one thing I'm going to do is, I know where the start point is, I know where the end point is of that line, and I know where this new point is, this middle point. And if I plug those in order, so hold shift down, 1, 2, 3, I get a new, so it's like sort of like pulling the string on a bow. Okay, so now I've got a curve that's dependent upon that original line. So if I like manipulate this line, okay, what can I do with that? Then I could do some distribution on it. So I can divide that curve. And I've got one curve here, and we'll do another curve back all the way to this one. So I've got two curves, okay? And the simplest way to draw a line is with 2 points, right? Well, I've got 10 points here, or 11 points, pardon me, and 11 points here. So I can start to make connections between them. Now, it's not very smart right now. I probably want to do some more parametric stuff here. Oh, I want more than that. What am I thinking? Go to natural numbers here. Plug it in for n. Oops. Okay. So then I can kind of figure out if there's like a particular ratio that I want. Seems kind of like angled a bit, but I can play with that later. But so now I've got this curve that I can begin to manipulate. I can change the height of it, I can change the length of it, I can change the distance of it. And if I have 2 of these, I can begin to experiment with these kind of like suspension bridge kind of mechanics. So just as kind of a way to sketch one of these ideas. The other way you could do this, right, would be maybe to actually draw one like arbitrary line and have it respond to a parametric line, okay? But the idea that you can play with the way it's cabled, you can use that to distribute lines, okay? The lesson here that I want you guys to pay attention to, A, is the like topographical part. So this idea that you can there's a reason why they say like construct point, deconstruct point, and it's not just to annoy us, is that sometimes we have to use one kind of geometry to find another kind of geometry that we want to use. Okay? It's almost kind of a trick. It's like I've got a surface and I want to get points out of it. How do I do that, right? Or I've got a line, how do I get the points out of it that I want so I can make something else that I want, right? And so in this case, like understanding how the mechanics of the line works, allows us to kind of make this kind of construction. Paying attention to the states of the program, like kind of keeping track of like, okay, this is the original line that we made, the SDL line. We created a new, curve by extracting points from it. So this is actually the top chord, and this is the bottom chord, right? And then now connecting these sets of points together to give us the lines we want. So just keeping track of the state of things that we've got is always important. Okay, so that's just an example of that kind of mechanic. And so different ways of using distribution to create form. Okay. So I think I showed a railing example. So this idea, and even the cabling on this is actually could be a pattern. Like you could have a really, you could start with a lot of cables, and then you could just cull, subtract them, so that you end up with pairings of cables on your bridge. So even there's kind of a pattern that they created. Look at the spans between. So you've got this piece right here that's actually angled, and this other companion piece. And look at the spans between there, that there's some kind of beam that they use to kind of span them. If you found the points on those 2 lines and you connected them together and you swept a profile across them, right, you could basically like parameterize this like backbone as well. And the railings that go along this. So remember the example I showed you on the very first day of that stadium, right? And you think about like how they started with a radius, and they copied it and they scaled it and they copied it and scaled it, copied it, scaled it. They got all the points and then they started drawing curves between it. It's a really common way to think about creating this geometry. Think about how many there's like this base curve, this curve, and that curve, and all the different ways that those connect to each other, and the ways that they're like selecting the points along those lines can completely create this bridge. And once you've got that sketch, right, you can just play with it. You can talk to your professor and kind of figure out like what kind of idea you want. So it's a really powerful idea, okay? And you can kind of noodle with it. So you can start with this bridge, and you can start with a known bridge, and through parametrics modify it into something else. All right. So a couple other projects here. You guys know this one, the British Pavilion by Heatherwick? I see some nods here. Okay. So this is kind of amazing. It's 2010, but it still kind of amazes me. So this is the outside, and that's real. It's not a rendering. God, it looks like a rendering though. It's kind of ridiculous. This is the inside of the pavilion, and what it is a bunch of seeds that are placed inside of these glass. I don't want to call them tubes, I guess, but these like fibers that go from the outside to the inside, and they kind of act like fiber optics, like they actually kind of bring light in to sort of illuminate these little bundles of seeds, right? So it's a really amazing kind of structure, and what that is, right, is essentially a distribution problem, okay? This is basically a big chamfered cube, right? The edges have been like rounded off, and and then there's an inside surface, and these things have been distributed along the inside of that surface. I'm sure it was computational. Like there's no sane way to do it otherwise. So let's talk about that. We talked about how to use curves as a distribution element. Let's talk about how to use a surface as a distribution element. So you can start with any kind of arbitrary like surface. You could take an object and explode it to use it as your surface. Because from a topological level, right, any kind of object, like let's say a cube, right? Let's say I would make a cube. If I'm Heatherwick, right, I might start with a cube. Is actually 6 surfaces, right? If I explode it, right? Top, bottom, 4 sides, okay? So you can see even on the inside of it, it's actually hollow, right? It's actually just 6 surfaces that are facing outwards towards us. So, but let's focus on one surface. So anyway, from a topological level, solids are surfaces, right? We can break down a solid into component surfaces. Once we have a surface, we can do all kinds of stuff with it, right? So we've got, let's just say we start with a surface. You can reference a surface, like most other objects, in Rhino, right? You can go ahead and hide it. And there's different ways. So we've got this surface. Now one way to get like an object on it that's really like simple, right, is to just, there's one way to get a point out of it, right? I can put, that's really funny. Oh, it's using that as a centroid. Okay, maybe I can do area. Got to watch the difference between, yeah, okay. So if I do area of it, I can find the center of it. And again, once I have the center, I can find an XY plane. Oops. And then I can put, maybe I'll do spheres. I'll put a sphere there. Okay. Let me hide these here. It's getting really complicated. Okay, so I can put some object on it. But that's kind of dull. What I can do is I can do things like I can say surface points. So I can actually find points on a surface. So now I've maybe got the corners of that surface, and I can plug those in, and I can distribute things to the corners. You know, maybe that's not so exciting. When it starts to get interesting is when you can divide a surface up, and this is a pattern that I want you guys to know. We'll use this one all the time. So this is the divide surface pattern. So you're going to start with an iso trim. An iso trim wants a surface, and it wants a domain, and the domain is basically instructions for the butcher to like chop up this beast into cuts, okay? And you'll see this a lot. I'll show some videos or whatever. So eventually I'm going to start glossing over it because it's just such a common thing to do. So we take a surface, and we find that it wants a domain, right? Now what we want is deconstruct domain squared. Wait a minute. I don't want that one. Once again, they have changed the names of my things. Maybe it's construct domain squared. Nope. Bear with me here. Hang on a second. There's only 4 choices, so eventually I'll find it. If I go to math. Yeah, I want to construct the domain. Nope. Hang on a second. Domain squared. Divide domain, that's the one. Okay, so divide domain, pardon me. Okay, so this one, divide domain squared, divide. So just type in divide. Starts with some base domain, which we're going to get from the surface. And then we have these UV segments. And UVs will take a number slider. Basically tells us how many pieces we want. It's like how many ways do you want me to cut this up? Okay? And I'll just do these as from 1 to 20. Use whole numbers, like no fractions of things. You can't have a fraction here. And we'll make a copy of this. Okay, so we got now you got a domain. If we increase the numbers here, it'll look like something. So we've got 0, U to this. So basically a bunch of UV domains. Okay, and if I plug those in for the domain, and I plug in the surface, it basically cuts up my surface into a nice bunch of squares, right? So it's like we're cutting cake or something. And you can play with a number of panels. So lots of things you're going to see, kind of, when you think about computational projects, a lot of times you think about these panelized things, right? That there's some kind of folded surface, and it's been like divided into cubes, and the things open up. The very first step is to just take that arbitrary surface or that parametric surface and start dividing it into panels. And this is the first step. Okay, so this pattern, like these 3 components, is a really, really key thing. This will work for any arbitrary surface. So if I take some like whack-a-mole kind of let's just take a couple of curves. Actually, I'll just make, yeah. Site. Doesn't have to be flat, doesn't have to be square. Particularly, it works really well with lofts. So if I just had like a lofted surface here, right? So now that's starting to look, and it's just like a sheet that I can begin to divide, okay? And you can have a grain to it. If there's more divisions in the V than in the U, that creates a grain. U and V are what are there. So we have X, Y, Z and like typical coordinate space. U and V are coordinates that only, like on some topological level, this is flat, like in some kind of math land. And in math land, the coordinates are U and V, and U is X and V is Y. Okay? And so you can think of these as X and Y, but within the sheet, like if I was driving along this and I was like an ant or something, and I thought this was the world, this might be like flat to me, right? This might be flat. To us, it doesn't look flat at all, but in this universe, it is flat. So we can't refer to it as X and Y values, because X and Y is like all over the place, right? But if you want to find something that's like near the center of it, we could find the U coordinate and find the V coordinate. It'd be very easy to find exactly where that center is. We can turn these back into X and Y coordinates if we need them. But that's why they're called UV. It's not to like mess you up. It's so that there's a frame of reference on this plane. So again, U is the X, you can see. Right, that makes sense. V is the Y. And occasionally you'll find W, and that's Z in that local coordinate system. Okay? But you don't need to worry about that too much. Just know that that's why it's called what it is. Okay, so once we have a surface, then we can do a couple things. We can do deconstruct B-rep, because again, it's a B-rep. Even though it's a surface, it's still a boundary representation. If you plug in this component, this is great. This gives you all the faces, all the edges, and all the vertices in one component. So then we can do whatever we want with this thing, okay? And can be really useful. So if I turn off this surface here, so we can do a couple things here. You guys know the pipe command. We showed you this with the railings, the pipe. Okay, I can take a pipe and I can put all the edges into it because they're curves, right? And now I've actually got a grid. All right, I've actually got like a cage or a mesh or whatever. Okay, so very simply, again, any arbitrary thing, right? I can start to turn it into like a space frame. I'll show you some more complicated stuff with that later, but that's pretty easy, right? Because I have access to all the edges of it. I can access all the vertices. Let's go back to our little sphere that we had, right? And if I plug in that for where all the vertices are, I distributed spheres to all the vertices. Actually, if I go in and I go back to my pipe, I can create, and I'll reduce the radius here. So now I've got like more of a net kind of thing, right? So just very easily, and that's any surface that you throw at it, right? So explode, this is actually, it looks like an explosion. It used to be called explode brep, now it's deconstruct brep. But that's a really useful thing to have when you've got your surface divided up. You can start to play with that topology. The other thing that's really useful, so we played with the edges, we played with the vertices. The faces of it is another thing that's really useful. And here you can throw on an area component and you can get the center, and I think I showed you guys this in the video. I've showed you, I know some of this is like review, but I think it's useful. So you can get the center of all of those things, and this is where you can begin to do some really interesting things. And I think I showed you guys this with cylinders as kind of spikes, right? That I can take the centroids of that, and those are kind of planes. Let me increase the length here. Let's do these as, let's make it really spiky. Yeah, okay. Right? So you can, this might be like a forest or something. Like you've got some kind of like topography and you're going to place these things on it and they're going to grow straight up, okay? So, I mean, just as a way of, there's a lots of, as long as you can extract, points from it, you can start to distribute geometry. But the problem with this is that it doesn't like adjust with it. If you look at Heatherwick's, they're not just sticking straight out, like they're actually conforming to the shape of the form. That's actually what makes it interesting, right? It's like this big kind of puffy thing. If you look at these things in Rhino, they're all just like basically going up in the z, coordinate. Like they're not like flowing. They're not doing anything really interesting with it. Okay. So there's another pattern that I want to show you guys that looks at. So basically these are all whether it acknowledges it or not. It's basically just a bunch of XY planes. So you can see that they're just like terraced here. So the XY planes, if you don't have anything, it defaults to XY. So it stuck a bunch of XY planes on those points, and it stuck the columns on it, and it's not moving at all. In fact, if I zoom in really close, it's physically not really possible. I'll hide these again. See, it's actually hovering. It's actually not intersecting the ground. It's kind of hard to see, but yeah, you can see the gap underneath that. So that's not really like useful to us. I mean, we could maybe bury them a little bit deeper, but what if we wanted something to actually like adjust to it the way that Heatherwick's does? Okay. What we need to do is find a way to make those planes actually flow, because each one of these surfaces, right, is its own. I mean, each one of these little things is a surface, and it's really its own plane. Right now, we're treating it as if all these things are the same plane, and that's not very smart. Okay. So what I can do is I can evaluate a surface. So just like we can like look at a curve and we can find out where a point is along a curve, or we can find out where the endpoints are, or we can take explode brep or deconstruct brep, we can find out where the edges are, where the points are. We can find out other information about the surfaces, such as what plane it's in. Okay. And so what you do is you plug in a surface, and then you plug in the UV coordinates of that surface. So here's where we actually start to need some UV coordinates. And don't worry if you don't completely understand it. It's mostly just to tell you why I'm doing what I'm doing, like what the pattern is. The most important thing is the pattern. Okay. So we'll start with the surface, which is actually multiple surfaces. I'm going to take the faces and plug it in here. And then I've got this. And then I've got the centroids of. So each one of these surfaces, right? There's 48 surfaces. I want to take the centroids, which are the center of each surface, and I want to look, and I want to get the closest point. Let me make sure this is all clear here. Okay. I need the UV coordinates. In order to get the UV coordinates, I need to go back to the surface I cut up. I need to find the closest point on that surface to the surface that I cut up in the center of that surface. So I take the centroid, plug it in for, and actually something's around here. Let me just go ahead and flatten these. Hang on a second here. Oh, base surface. I got that backwards. Okay, point, surface. That's better. Okay. Don't get that confused. Okay. And actually, I'll just go ahead and yeah, keep the same level. Okay, so I've got all the points, all the surfaces, and it gives me all of those UV coordinates. So I plug in the UV coordinate, and that gives me, look at these things, local planes. See how they're like adjusting to it? So instead of these like dumb planes, which are just flat, I've got these smart planes that are actually adjusting to the thing. And again, the technique that I did was, I need to evaluate the surface, because that'll actually give me those, they're called frames, but they're planes. In order to do that, I needed the UV coordinates. So I looked at the closest point on the surface, which is the centroid, and I extracted the UV point. And again, you don't need to know like any of that. Just, you can take this pattern, you can copy paste it, you can go play it back in the video. All you need to do is understand that if you want something to flow along a surface, this is the pattern that you want. This is how you get a local plane for something. Okay? So once I've got that, instead of the planes I was using, I take these frames and I plug it in for the cylinders. Oh, and actually that did something. Wow, that's kind of a cool structure. All right. What happened is that the height, I might need to do a negative height, right? Because right now the planes might be like flipped. And so if I do a slider that has a negative component, I should be able to get it to come out the other side. It's perfectly fine to have a negative number here, because all you're interested in is the depth of the extrusion. So let's see if that works. Yeah, that works. So it's like growing hair or something. So that becomes interesting. I'll show you something else that's kind of interesting. Maybe you guys have already seen this before, but if you take that original surface, and we need to find, so I want to make a copy of it, and I want to extrude it along its plane. So I'll do the same thing I did before. I'll evaluate the surface of the original surface, and I will find the closest point on the surface to its center. So this is just the one surface, the main surface. Okay, point, surface, UV points, and I get one frame, and I'm going to, so whenever we extrude something, we usually have a vector. We usually have a z or an x or a y, okay? But that's kind of arbitrary. What we can do is, if we evaluate a surface, we can actually get a vector that's only for that surface, that points like perpendicular to that surface. And so we can use that vector to extrude a surface in its own direction. So that's not that's not z, that's not x, that's not y. It's, TED or whatever the surface is called. It's that vector, okay? So if I take that vector, and I multiply it, because vectors are like unitary, like they're just one, which isn't going to give us much. So if I multiply that vector, so I've got a vector, which is actually the normal here. I might have broken this here. Don't tell me that, it's going to break. Reference surface, extrusion. Okay, and then I'm going to take the exact same amount that I had here. Yeah. So you can see, oh, actually, instead of extrude, I'm going to move it. Same principle. Starts with geometry, has a vector. I could extrude it, that would be fine, but I'm not. That's actually not what I want to do. So vector, geometry. Yeah. So I've actually got a whole connection of things here. Let me hide these. Whoa, not hide everything. Turn this on here. Do this, do that. Okay, and now I've got, wow, actually it's a little out there. but I could create something that actually has a connection between the two surfaces. This is kind of weird over here. I'd have to look at that.
Would you be able to like do the inverse of what you did to create the points for the beams?
Oh, I could actually just take and make points on the above surface and then connect the two together. Yeah. Did I show that in the demo video? Yeah. Let's actually look at that. That's a really good idea, Mason. So Mason's thing was if I found basically points on the other surface, why couldn't I just take the extruded surface? Yeah, why don't we do that? Let's see here. Let's get rid of all this. That's probably even more useful. Okay, and let's get rid of this. And let's see here. Okay. Yeah, give me 1 second here. So I do need the copy of this though. So what is? Oh, the UV is the broken part. Okay. So I need the closest point again. Yeah, this will be cool. Okay, so I'll take the center point, and I'll take the surface, and I'll take the UV point. Okay, so now I've got my two surfaces. So I've got this one, and I've got this one. And so I'm going to take this above surface here, and I'm going to do the same pattern that I did. This is actually really good because it's a good review of it. So I'll divide domain squared. I will do an iso trim. And I need the same, in order to get Mason's plan to work here, I want these to be dependent on each other. They should have the same number of divisions, because they're just copies of each other. And then I'll do deconstruct B-rep. So now I've got two, but they're extruded from each other. And I will take and find the centers of each of those setups. Good. So we'll take so now I've got two sets of points. Start to hide some of this stuff. It gets really visually cluttery there. All right. And now take Mason's idea and let's just draw a line between the two sets. So these are a bunch of A points and these are a bunch of B points. And that's pretty good. And then we'll just pipe it. Yeah. So that's pretty good. So it's kind of a substrate, and again parametric, and that's actually flowing along with the thing. If we decided not to do that, we could just have the things go straight up and down. But this will work for any kind of surface there. So that's actually a pretty good idea, as opposed to having them be separate, making them dependent on each other. All right. So I know it may be a lot to follow, but do you see how we reuse patterns? We just reuse the bridge pattern and the pipe pattern from the railings. We divided the surface. We found the local normal of that surface and we used it to extrude that surface. So actually there's a lot of different, this one really combined a lot of different patterns. So this could be the structure of something. This could be a detail that you then cut in section. Or it could be some kind of a parking garage, or just some kind of idea that you have. But fully parametric. If I made another surface, that's what's actually really cool about this. Hopefully I don't totally mess this up. But if I made a surface of my own, any surface, even if I go back to a flat surface, I should be able just to reference it. Yeah, and it's going to give me. So that'll work for any surface you throw at it, basically. Okay. So what's really nice is once you have one of these tools, right, you save it, put it in your toolbox, right, or you can give it to your friend or whatever, and you've already got this thing kind of, it's already been sort of pre-computed. Okay. You can use this in different parts in the same project. Let's say you have a park and you want to do different kind of surface effects. You can take different surfaces in that park and you can apply this differently to it. Okay. So it almost becomes a modular design idea. All right, so that's really, so the idea of Heatherwick's project, right, is that you could take this piece of geometry, let's say it's this chamfer thing or it's a cube or whatever, and if you find those normals of it, right, you can make those spikes come out of it, basically. I mean, in a really simplistic way, that's kind of what's happening here. He's finding the local normals of all these things and projecting them outwards with the same geometry. Okay. So you can do that kind of thing. I'm going to skip this project here. Let's go to this next one here. This is the Bard House. This is really similar to one of the projects that I saw from Scandinavia. I don't think it's not in Scandinavia, but you can see this idea of this masonry pattern. It's almost a checkerboard pattern, but it's sort of creates like a relief. You have these bricks, and some of them are, you can either say some are pushed out or some are pushed in, but it creates these really distinct shadows. And different times of day, different ways you look at it are going to produce different shadows. It's a very simple idea. But in application, it's really kind of a stunning texture for this building. You know, the fact that it's all white material, you get this kind of effect. Like when you just have a shadow, you don't see the joints anymore, and you start to see just kind of graphic patterns that show up in it. Okay, so like, you know, we can prototype that. That's actually something that we know how to do, like pretty easily, really. I'll show you. And that's actually going to... So go back to our patterns again. And I'm actually going to go ahead and start with a front panel this time. And I'll do this a lot. I'll just take an arbitrary surface and start to play with it. So we're going to use our... You're going to get tired of this pattern here. So we're going to do the divide pattern again. So again, divide domain. Isotrim, because what we're looking for, right, is this brick pattern, and this will, you know, once we get this going, you could apply this to any. You could basically take this project and divide it into surfaces and apply the same like pattern to each side of the surface. Okay, so like this is a surface, you know, that's a surface, the other side of it's a surface. So once you've got that, do that. And I'm just going to leave. I'm not going to play with the UVs yet. I'm just going to go to the idea of it now. What we're seeing, though, is that every other brick is extruded, right? It's not every single like brick. Okay, so what did we do that allowed us to just operate on a certain percentage or a certain pattern of a collection of things? If that makes any sense. Like, how do we operate on a subset of this? Yeah, the cull pattern. Okay, so there's lots of different ways to use cull. You could, you know, the easiest way might be to do something like cull nth, and because cull nth by default says cull every other one, it's basically cull every second one. So if we plug that in, something's wrong with this though, right? Like we've culled it, see the green part's what's left, and what we've ended up with though are like bands, which might interest you. Like that might be what you're after. But what's wrong with it is that depending upon the number you have, whether you have an even number or you have an odd number, right? It's going to give you a different result. But if we set this to an odd number, we'll get the pattern that we want. So that's actually one of the reasons why when you make these like sliders, I doubt we've ever done this before, but you can specify, you know, even or odd numbers. So that, except for the first edition, you know, should always produce the right result. So we never get an output that's wrong, if we know that that's part of the pattern. Does that make sense? With a cull, if we have an even number and we cull every other one, we get bands. So we want a checkerboard. So we want to make that built into the program. Okay. Okay. So from here, we've got our wall, and then we want to extrude it, right? So we take extrude. Extrude takes a vector. What direction we want to extrude it in? Yeah, the y direction, right? So let's throw a unit y on there, and we'll plug in a slider. Notice that y is positive in this direction. So if we want to extrude it like towards us now, we need a negative number slider. It's pretty. If you don't get it right, you'll figure it out because you can basically just see it and then you'll change it. But it's good to kind of know ahead of time if that's what you want. So again, if I extrude that outwards, and I may have talked about this, but I don't know if I have. But if you want to get something in Rhino, you actually have to bake it first. So if I bake this geometry, yeah. So then even if I close down Grasshopper, oops, didn't bake that one. Let's bake it. I don't know why bake. Bake is like a fried egg, which never made sense to me. Okay. So in order to get something real, you actually have to bake that state of the geometry. But now you can render this, you can cut it, you can take a Sawzall to it, you can cut a window in it, you know, like whatever. But there's a very quick way to do this. Now, what if I had, you can delete this now. Going back to my crazy, whoa, that's actually the wrong direction. If I had something like this, and actually this is something that I've noticed in the new version, yeah, is that I used to take these as surfaces. It doesn't like them anymore. If it does that to you, just call it a B-rep. It's extremely frustrating. Like that's a surface. It doesn't need to be flat to be a surface, but B-rep is fine. It accepts that. But you'll notice this has the same problem as the other one. Like if we extrude it in the Y, it only extrudes it. Let me actually just bake these. It's a little bit hard to see. Bake. And bake. Okay. So you might be okay with that, but it definitely is not the same. It doesn't flow like with the surface, right, when you extrude it. Okay? So this is where you need that pattern that we just showed for like Heatherwick, where it's going to adapt to the surface, to the local coordinates of the surface. Right? If you just extrude it in the Y, that's what it does. It's just going to take a straight line and like pull it out in the Y. Okay. What if your thing starts to go around a corner, right? And now it's actually in the X, right? Or what if it's in the negative Y as it goes around? So that's why that like Heatherwick pattern is really useful, because it adjusts to whatever. It doesn't need one of the three cardinal vectors. Each one of it has its own vector. Okay. And so if you were going to play with this idea or something like it and make an extrusion along the surface, that's where the Heatherwick pattern makes a lot of sense. It's actually going to make a lot less work for you, and it's going to look right. I mean, maybe you want this. I don't know, but this is only going to work for this particular axis, and it's just not. It's like pushed out, So there's a difference, right, between the cardinal vectors and the local vectors, and that's what you're going to get. Okay. I'm sure nobody wants me to show you the pattern again for that, but you would apply the Heatherwick pattern to that. Okay. You guys know this project, Peter Zumthor? It's in Poland, and it's this beautiful kind of masonry. It's attached to some ruins. It's kind of like Valls-like. You guys probably know that project, but it's a bunch of stacked masonry, and it's done such a way. There's a rhythm to this, but it looks pretty random, right? And they basically like strategically not placed bricks, and it creates these really great kind of light patterns. I mean, it's a really beautiful image there. So like, how can we create something like that? There's a couple different ways. I do not usually talk about randomness until later in the course, because I think it's important to get a handle on logic like first. Not that randomness isn't logical, but I think it's too easy just to play with stuff. So, but one way that I do use randomness, that I will show you how to use randomness, is with the random cull component. So we're going to go back to this, and actually, in order to make this work, we're going to need a lot of these. A whole lot. Let's do 200. And yes. Okay. So we're going to attempt a Zumthor here. We'll see. Oh yeah, that's a lot. I might need a bigger. I might slow my machine down too. Yeah, 120 by 120 is a lot. That might be too many. Okay. Let's do 50 by 80. It's one thing you'll learn about things like Grasshopper. At least for the time being, there are some limits. Like it will start to slow your it'll start to slow your machine down. Okay, because I want a lot of things because I want to get an effect like this. And what I'm going to do is I'm going to grab the areas of all those little surfaces so I get their centers. Now I've got 4,000 centers. Okay. Hang on a second here. This is like two. Okay. Scale. Let's make it 3 times as big. It's the beauty of parametrics too, right? When I scale that geometry up, then it automatically propagates. Okay, so I've got that, and I'm gonna I'll do it with rectangles. I'll behave. Okay, so if I take that, I take these. That's where all the rectangles are going to show up. The rectangles are going to be wider in the X than in the Y because that's going to be like a Zumthor brick. See, zoom in here. Oh, they're on the wrong plane though. Okay, so what? They need to be in the ZX plane. So we'll make a plane and then distribute it this way. You can see the ZX here. Let's take a look at these. If it doesn't show up, oh my goodness. Okay. Yeah, you can see. Yeah, so we've got like a sea of rectangles. Okay. Then what I can begin doing is let's do cull pattern. Well, there should be a random cull. Yeah, random reduce actually is not. It's basically acts like a cull, but it's not called a cull. It's called random reduce. And so basically, you give it a list of numbers, and it'll just start to like randomly like decimate that list. Okay, and it's kind of a nice form of controlled randomness. So I take my list of 4,000 rectangles, and I plug it in for my list, and then R is the number of items to remove. So I make a number slider. I've got 4,000. Let's crank it up so that maybe at the most we want to remove half of them. And if I plug it in, you watch what's going to happen here. Again, not as disciplined as what Zumthor's doing, but starting to get that effect that it's sort of like dissolving. Okay. So another thing that is a way that randomness works in Grasshopper, and it works a lot of ways in different randomness algorithms, is that you have a seed. So I took a list and I asked it to remove 1,660 items. What if I don't like that? Well, I can plug this in for S for the seed, and the seed is like some number in the algorithm that makes randomness that you can actually control, and so it creates a different kind of randomness. So I can actually scrub this, and it's just basically going to give me like different states of that solution. So it's essentially parametric randomness. Like if I gave this algorithm to you, like if I like this thing and I wanted you to have it, right? It couldn't be truly random, right? If I give you these settings, you should get this output. So that's the way this thing is set up. Okay. So if I give Lauren or like if I give Emily this, they can have my settings. If they decide that they like setting number 900 or whatever, I can't even get to it. Type in 900. That's what you're going to get. It's not the way randomness works, obviously. It's not a roll of the dice or a spin like the roulette wheel, but it's functionally equivalent to randomness. Okay. Now, maybe I don't like this. Like there's too many like rows and things. Like I don't like the way this is. You can actually take that list and reduce it too. All right, so I can actually go in. Should be able to. I might have too many of these. Yeah, I forget. With cull, you gotta be really careful because it's like the two are on top of each other. So I can actually I can cull a list that I've culled, or I can take this and I can cull it by some pattern. I can remove every other one, but you don't have to be stuck with like one instance of it, right? This is a state-based program. So I can randomly reduce it, or I can reduce it as a pattern, and then I can randomly reduce that. There's lots of different ways I can play with it until I end up with the result that I want. So I've actually got a lot more control, here over it. Does that make sense? It's just the same algorithm, Mason.
Can you set up parameters like if you wanted to make a brick wall so that they're always touching each other, so that it would be much less stable?
Yeah, I mean, basically, like in the example that I gave for homework, right? I did a call where I removed every other one, and then I gave them like spacing. If you got the right proportions, like the size of the brick, and you could say like, okay, you could do a pattern call. And I don't know if I showed you guys this one. I don't remember if it's in the video, but one of my favorite ones is a pattern, called pattern. And if we were programming, we could just write a program that says check every brick, make sure it's touching a neighbor, or check every brick and make sure that there's a neighbor that's 3 bricks away. It's a little bit dicier to do in Grasshopper, but we can fudge it. So I could take something here, and call pattern is really great because you can go in and you can say, so instead of having an nth or random, you can actually say, okay, remove 2 and then keep 2, right? Or you can say like remove 2, or like remove 3 and keep 2. You can do any kind of pattern you want if you can spell it correctly. Yeah, you actually do have to. Well, so you're basically going into set booleans. Try to do this correctly here. So it's 2 off and 3 on. And actually, in this configuration, it's going to give me that pattern. This is one of these things where I have to like play with it. Or maybe that's what it's going to give me. So I need a better looking pattern, basically. Set booleans. Let's see if that doesn't. Yeah. So you can actually start to create more complicated patterns. So Mason, if you did that, Mason, and you extended them a little bit, like that would actually give you a different kind of wall. So that call pattern is really, really useful too. And then who's to say I couldn't take that and start reducing it randomly too? Okay, so really these calls are really interesting. A lot of times we think of like patterns as something that we have to set up a rhythm, like we have to say like I want something and then take a pause and then I want something else. But in this one way to do it here is just to start with like everything and then remove the stuff that you don't want. Okay, so instead of an additive process, it's actually a subtractive process. Okay. It could be a little bit easier. You can certainly set up rhythms with this, right? Like the example that I showed, in the very first thing. This railing thing is basically a call pattern, right? So true, false, true, true, false will actually give you that if you have those railings, if you have those the rails. Okay, that's how you actually make that. And then it becomes to change the pattern, just change the call pattern. It becomes really easy. Okay. So that's kind of logic I'm talking about right now. It's not exactly that complicated, but it definitely. So, if you got the right proportions of the bricks, and you like turned off the right things, you can also use cull to like select things, right? I think maybe I showed a pattern like that. Let me see here. I'm gonna turn this way down. One of my favorite things to do with it is to use it for, so I've got, get rid of this rectangle now. Let's take a look at this. Okay, so I've got these planes. I can take a circle, and I can take a polygon. So the two kinds of geometry. And I want to, I'll do a cull pattern. And one pattern I will do false true. And the other one I'll do true false. So just delete that one, do true false. And if I plug these in for the same thing, you can see that now I've got these two different sets, right? I think I still have too many, or not enough objects. Maybe that's what it is. That's much better. No, it's Christmas. Okay, and I need an odd number here. Yeah. And I have a checkerboard. Okay, and I can plug these in. So I can take these planes and plug them in for circles, and these planes and plug them in for polygons. And I need to increase the radius a little bit. Maybe a lot. That's what happens when you don't have a scale for anything. Okay, let's turn these planes off too. They're too similar. Okay. Let's do a three-sided polygon, otherwise known as a triangle. Okay. And then now I can do patterns. So just by basically flipping it. So I've got one pattern. Turn these back on. So the evens and the odds. So cull is a way to set up patterns. You could do the thing where like every two is a triangle and then every third one is a circle, and you just go crazy. You could do 3 patterns. You could do 4 patterns, and you could have like a repeating pattern of these things, right? And this will work like, let's say you have a surface that's flowing. All you're doing is taking the like distribution and basically tweaking it a bit. So you're saying I want to select a certain number of these and not a certain number of those. And you can create these really complicated distribution patterns. Okay, so it's a useful patterning thing, but don't have to. It's not wallpaper. You can think of it spatially. Okay, this could become a facade. This could become like turf. This could be a canopy for something like that. And that's actually where I want to sort of end it here. I got this project here, the Städel Museum. So it has this really interesting. First of all, the proportions of this are kind of based on the exterior of the museum, but then as you go onto this lawn, it has this great kind of night reversal where it sort of like illuminates this parkway, but it's also like bringing in daylight down into the gallery space, right? It's just like diffused daylight. It's very mod. It's very like and even everything in the thing, even down to like the speakers, and the air registers had this like pattern in it. Like it's a little bit over the top. But thinking about like how you would do that pattern, you guys remember what we did in Studio, where we start turning some of the stuff off here, where we did points. It's not going to let me construct point. Okay, construct point, series. Zoom back in here. Okay. So let's say that I did a series of these. And I'll go ahead and graph these so I get a grid. And the thing that I really want to mess with is the z-coordinate. So what I'm trying to do is recreate this kind of shape, this kind of bulge. And we actually know how to do that. So I'll do graph mapper and range. And this is another pattern, like if you want these kind of hyperbolic shapes, basically you can start with something like, you could do a parabola, or you could do a sine wave. And I just like to do this, or just kind of make it a hump, okay? And then if I need to multiply it because it's always going to be too short. It's always from 0 to 1. So let's add a multiplier. And we will sort of start getting some output here. Let's give it a little bit more juice. Yeah, okay, so we got that. And just construct. And in this case, okay, I had you guys do 2 graph mappers to create the kind of paraboloid surfaces, or the kind of combined multiplied surfaces. I want the same thing in both axes. So actually I can just duplicate this one. So I can take the multiply component. It's kind of a trick, basically. So I take this once, and I take it again, and then I'm actually going to graft it. And that's going to give me the 121. Now, the issue here, though, is that we've got 100. So I actually need to, let's just combine these with a number slider. Same pattern we've seen in the homework. you want to take the count and make whatever range you've got one less than that. So we'll go in and just add an expression in -1. So when these things start to become automatic, that's good. Like it's good to just be able to tune out, because then you can think about other things in the design. Like it's good to start thinking in terms of patterns. Okay, stop seeing the components, like stop seeing the steps, and start seeing the larger picture of like the design. Okay, so that's why I like repeat myself, and that's why some of the assignments overlap, because when if you're an expert, you're actually not thinking about this part of it. What you're thinking about is the design. You're thinking about the next step. Okay, and so it's good. It's good to see these things in multiple contexts. Okay, so now we got this pattern, but it's way too big. Let's bring it down a notch. Aha! Kind of exaggerated, but it's there. Okay, let's give it a little bit more turf. Higher the resolution, the better. Okay, now, to review. This is just like what you guys did. I think in your example it was like a wall, okay? It's just a grid of points, x and y. I grafted the y to get the grid. The z is actually what we're changing, right? It's actually where the points are being disturbed, like up and down. And so for the z, I made a graph mapper, like paraboloid. I multiplied it because you need to multiply it because otherwise it's going to be flat, basically. And I took one copy, it's basically going like this way in one axis and this way in another axis. And if you kind of interpolate them together, right, you get this like bulge. And I do that by grafting the multiplier. So instead of 20 values, I get 20 times 20 values. Okay? And then if I've got 20 times 20 values for the grid, I happen to have 400 z coordinates. I get my mound. Okay? Now I've got points, so to make that into something, I can actually do surface from points. So I plug it in. And the issue is that it needs a number of u points. It needs to know how many points in the u direction. Well, I've got that. Well, actually, I've got it -1. I think is the problem here. Oh, and actually, I need to flatten this. Yeah, because the structure of it being the grafted structure has it as 400. Like it says 400 things, and it's 20 things that have 20 inside of each other. The 20 rows. We want 400 like raw points. So if we flatten it again, now we get it back to a surface, and that actually gives us the mathematical surface. Okay, so we have to remove the structure in order for it to begin to talk to that. So that's a pattern. Like I wouldn't worry about that too much, but that's a pattern. Once we have that pattern, then we can do all the stuff that we've been doing, right? So we can divide domain once again. And then we can do an isotrim. And then we can start to do things like finding the area of those things. And then we can take circles, place them on those things. Now this is where our pattern's not gonna work, so we need to evaluate. Because it's right, this one really doesn't look right. They're really not in the right orientation. So we're going to find the closest point on the surface to the area, plug it in for UV. Oh, I did it again. I did it backwards again. Gee whiz. The order's wrong. Okay. Too many things here. Okay. It looks like a lot, but it's, because it is. We've got 100 frames. If I hide the frames, you can start to see that. And actually, if I go ahead, I'm going to go ahead and reduce the size of these. So you can actually start to see these on the surface. Okay? And then what you can do, and I think this will work, is I can trim the surface. So I can actually cut it out of the surface. I've got to remember the right command here. I don't want to say divide by surface, but divide surface? No. There's our split surface. Yeah, surface split. Okay, so I take the original surface all the way back here. This was all just a process so that I could get these circles like where they needed to be. I don't really need the individual surfaces anymore. I want to treat it as one piece of turf. And then if I plug in the curves, this is going to take a little bit because it's actually subtracting it. Now it doesn't look like I've done anything, but if you drop a list item component, you actually just get, I'll hide everything else here. You get your Swiss cheese like piece, all right? And that's parametric, so I could go in and like change the size of it. I could change the like curvature, and it's going to redistribute. Now it's going to be slow as heck, okay? Because it's going to have to crunch through like all of this. Again, don't be like bewildered by like trying to follow it. Just take it step by step. Think about the process that I showed. Like for instance, you don't even know what this does yet, but just know that once you split the surface, this is how you get it out. Okay, that's the last piece you need to pop that surface out. I go ahead and bake this. You know, that's ready to build. Like basically, like that's a real thing. Okay, so you know, with these kinds of ideas of like paneling and like subdivision, there's a lot of opportunities you have for your designs. I encourage you guys to explore it in studio. If you have questions about how to do something, let me know. But look at the video again. Look at the patterns and how the patterns adapt to each of these like precedents. Okay, and start to look at precedents on your own and see if you can decode them, especially things that have like a nice repetitive pattern. Okay, and we'll do this one or more times here. I'll take you through some actual projects and try to give you the kind of, these are the big ideas of the project, right? It doesn't give you the whole thing, but it's a major idea, okay? And then there'll be a skills video posted this evening. Please look at it before lab. That's it. I'll see you guys later.